So in the last video, I talked about how to use arcsine and arccos and arctan, the inverse trigonometric functions, in the context of a right-angled triangle. This time I'd like to talk to you about them as functions. So recall, we've seen what the curve y equals sine x looks like, and what the curve y equals cos x looks like. Arcsine is just the inverse function of sine x. As soon as I say that, you might be looking at this picture and going, wait a second, you can't take the inverse function of a function that fails the horizontal line test. You fail the horizontal line test if it's possible to draw a horizontal line which touches the curve more than once. And of course, here we can draw a horizontal line which touches the curve infinitely many times, since sine just keeps oscillating up and down and up and down. So you might say, there is no inverse function for sine x, and you would be absolutely right. But what we do to make it possible is start by restricting the domain. We look for an interval of x values upon which the original function sine x is 1-to-1, where it passes the horizontal line test. And there are many choices we could use there, but the one that's usually chosen starts at negative pi over 2 and goes to pi over 2. So we only take this piece of the curve. Just that much right there. And of course, when we take that much, our domain is negative pi over 2 to pi over 2. Those are our x values. And our range, which are the y values, are negative 1-to-1. To take an inverse function, we take the curve of the original and reflect it over the line y equals x. I don't know if you can see what you get if you reflect that over the line y equals x, but you end up with something that looks very much like this. It goes between x equals negative 1 and x equals 1, and it goes between y equals negative pi over 2 and y equals pi over 2. This curve goes through the point negative pi over 2, negative 1. So this goes through the curve negative 1, negative pi over 2. And over here we have the point pi over 2 comma 1. So here we have the point 1 comma pi over 2. The x and the y coordinates just switch roles. You end up with a curve that looks very much like this. So this is y equals arcsine x, or you can write it as arcsine x like that, sine inverse of x. And the domain of this function is negative 1-to-1, what was formerly the range. And the range of this function is negative pi over 2 to pi over 2. The set of y values that come out here are what were the domain over here once we restricted the domain. We can do the same thing to cosine of x. Again, before we can take the inverse function, we need an interval upon which the curve is 1-to-1, where it passes the horizontal line test. Now, if we take the same interval, we can see it doesn't work. You can, between negative pi over 2 and pi over 2, you can draw a horizontal line which crosses the curve more than once. And again, there are infinitely many choices here. But the one that's usually chosen starts at 0 and goes to pi. So we take this piece of the curve right here. And again, if you reflect that over the line y equals x, negative 1-to-1, just like before. We're going to start at 0. Here's pi over 2. Here's pi. This curve goes through the point 0, comma 1. So this curve goes through the point 1, comma 0. And it goes through the point pi, comma negative 1. So this one goes through the point negative 1, comma pi. And it looks very much like this. This is your arccos curve, your inverse cos curve. Y equals arccos x, or the inverse cos of x, arccos. You can use the same words no matter how you write it. And again, what was formerly the domain, so the x here goes between 0 and pi, that becomes the range over here. Y goes between 0 and pi. You can see that the y values that come out are between 0 and pi. And what was formerly the range, which is still -1 to 1, that's the domain over here. So what we have here are the graphs of the arc sine curve and the arc cos curve. You can see the domains and ranges, which are just the reverse of what the domains and ranges are in the original function once we restrict the domain. Now I want to take a look at one more inverse trig function, and that's going to be arctan, the inverse of the tan function. So hopefully you have this all in your notes. Let's erase this. And I'm going to erase what's over here also. You can always pause the video and copy it down. And let's remind ourselves what the tangent function looks like. So pi over 2, pi, 3 pi over 2, 2 pi, and so on, minus pi over 2, minus pi. And you recall that the tangent function has a vertical asymptote every time cosine is equal to 0. So we have a vertical asymptote at pi over 2, one at 3 pi over 2, another one at 5 pi over 2, which is off my picture, another one at minus pi over 2, at minus 3 pi over 2, basically every pi starting at pi over 2 and going in both directions. And in each one of these spaces, we have what's called a branch. And there are infinitely many branches. This goes on forever. So this is y equals tan x. And again, the tangent curve fails the horizontal line test. This is not a one-to-one function. So if we want to take the inverse, we're going to have to restrict it to a domain where it is one-to-one. There are infinitely many choices you could pick. This is the one that's usually chosen. This is called the principal branch of tangent. That much. So we're going to take our domain to be negative pi over 2 to pi over 2. This time I'm using parentheses because I can't include negative pi over 2 and pi over 2 in my domain. The curve isn't even defined there, the original tangent curve. And my domain this time is negative infinity to infinity. It's all the real numbers. Unlike sine and cosine, this has no amplitude, or we could say it has an infinite amplitude. So we're going to take this, reflect it over the line y equals x, and see what it is we get. You end up with a curve that looks very much like this. Here we are at pi over 2, y equals pi over 2. Here's y equals negative pi over 2. And let me just draw in these horizontal asymptotes. What were vertical asymptotes now that the x and the y have traded places, which is what always happens when you take an inverse function. What was formerly a property of x now becomes a property of y, and vice versa. I don't know if you can see what happens when you reflect this over the line y equals x, but you end up with something that looks a lot like this. And this is y equals arctan of x. You can write it like that. You can write it like that. You don't have to put the x inside parentheses. I just am right now. Our domain is negative infinity to infinity. And our range is going to be negative pi over 2 to pi over 2. You can see again that our domain and range from the original function to the inverse function have just traded places. It's ironic that this curve, which is probably the least nice curve in terms of continuity, has the very nicest inverse function. This inverse function, arctan, is defined at all values of x, unlike inverse sine and inverse cos.